Okay, now let's talk about the signed multiplication. So far the algorithm we described is for unsigned multiplication. What we need to do first of all, we need to, for the multiplication circuit, what we need to do it in a two-step. One is that convert the problem as an unsigned multiplication problem, use the unsigned multiplier, then apply the signed bit. Okay, the strategy works fine because let's say you are doing a two negative value multiplication. What we can do, we can take its absolute value, pass it through unsigned multiplier, let's say minus 5 and minus 4. So your absolute value is 4, 5 and 4. Multiply them, become 20. Then we determine what sign it should be. So we know by algebra, two negative number multiplication gives a positive result, right? So we apply a positive sign there. Similarly, if there is a one positive and one negative, we know the sign of the multiplication product is going to be negative. Okay. So in this case, what we do, we first take the multiplicand and multiplier and pick up its absolute value. How we are going to do it? We are going to compute the 2's complement of the multiplicand. Okay, how do we do that? 2's complement, you remember, we invert the bit pattern and add 1 on top of that. So we deploy a 32-bit adder circuit with a 32-bit inverter for addition of 1, and that becomes your 2's complement. And then you pick up, based on the sign of the multiplicand, either the multiplicand itself or its complemented form. Okay, so if my multiplicand MSB is 0, then I pick up the multiplicand itself, because multiplicand 31 0 signifies that it's a positive number, because we are all talking about 2's complement number system usage here in the computing system. Now if the multiplicand is 1, MSB of multiplicand is 1, that means it's a negative value. For that I need to pick up its 2's complement, because remember, like in the 2's complement, the beauty is that if it is an bit pattern for a negative value, if you make it a 2's complement, it becomes a bit pattern for its corresponding positive value. Like if you are feeding in a minus 5 in 2's complement and you compute its 2's complement form, again it becomes a positive 5. So that the property we are exploiting here, that if my multiplicand is a negative, we are testing that, then pick up its complement form, and which is a positive. Similar thing we do for the multiplier as well. We pick up the, ultimately we pick up the absolute value, and then we do the 32-bit unsigned multiplier, which gives you unsigned multiplication, that gives you 64-bit of result. Now again 64-bit I need to take as it is, which is an positive value, or we need to make it a negative. Let's say result has to be negative 5, or let's say negative 20, and unsigned multiplier of course gives me the absolute value of 20. Now depending on what sign its result is, I can always make another 2's complement and make it a negative 20. But we need to decide what the sign would be. So if we take 0 as positive value and 1 as a negative value, then we can create a truth table, right? So positive is positive, so 0 0 is 0, negative is positive, that is 1 1 is 0, negative positive is negative, so 1 0 is 1, and positive negative is negative, that is 0 1 1. And if we construct the truth table, it's basically nothing but an XOR function. That's why we place an XOR, we do an XOR computation between the MSB of multiplicand and MSB of multiplier, and whatever the result, that dictates what I pick up, whether I pick up its true form or the output's 64 bits complemented form. But note, we need to deploy a 64-bit complement circuit here. We are not avoiding anymore your adder 64-bit, then 64-bit inverter, and 64-bit with 1, like value 1, we add them up. So we compute a complement of 2's complement format of this outcome being 64-bit from the unsigned multiplier. Okay, so we compute both of them and we pick up whatever result we want to pick up depending on the target sign. Okay, so that's your signed multiplication circuit. Just to correlate with the MIPS, whoever done the MIPS assembly in CS47 or equivalent classes, remember the mult instruction is basically like 60 will result 64-bit, right? And that's why it used to have these high and low register, right? Because multiplication of 32-bit is always 64-bit, so we need to have a place for 64-bit register which is high and low. But clearly, like our own CS147 DV, that instruction set architecture we are dealing with in our project that is described in lecture 1, this multiplication is not sufficient because we have not defined a high and low register here. The reason is that I wanted to keep the whole project and whole idea simple. Okay, so what essentially we are claiming that we support multiplication, but we support 16-bit because our format is like your destination register is multiplication of source register and target register, but all are 32-bit, right? And your destination register is also 32-bit, so it cannot simply hold a 64-bit 32-bit product result. So it can hold maximum your 16-bit product. Okay, 16-bit product. Unsigned. Even I'm talking about the unsigned product. Okay, so that's the limitation we'll live with in this whole semester for this project. Our target is to make our conception clear, okay, not really make a real life like 32-bit which actually does MIPS like multiplication operation, like supports 64-bit. Okay, anyway, the MIPS has, if you recall, it has high low, and we have like data movement from and to the high low, and we can check pick up both of the high low registers value and combine them together into a 64-bit result if needed. So that's the point I wanted to mention at this point.